Welcome to the session. Today we are going to discuss how to construct a spanning tree by using DFS and BFS algorithms. So from this, first one is depth first search algorithm, that is known as DFS. DFS algorithm starts with any initial node of the graph G. Whenever graph is there given, then from that we are going to find out a spanning tree. So the given graph is, let us we are considering it as G, and it goes to deeper until we find the goal node or the node with no children. So we are just moving deeper where we are going to start that. From there, if there is no children, then we'll go to backtrack and we are going to perform this operation. Now we are going to know what is the algorithm, how it is going to be traversed from one node to another node, that we are going to know that. So first, create a stack with the total number of vertices in the graph. So first of all, we have to create a stack which is consisting the total number of vertices of the graph. Now choose any vertex as the starting point of a traversal and push the vertex into the stack. Then after that, push non-isolated vertex or adjacent to the vertex on the top of the stack to the top of the stack. Now repeat 3 and 4 until no vertices are left to visit from the vertex on the stack of the top. If no vertex is left, go back and pop the vertex from the stack and repeat 2, 3, 4 until the stack is empty. So first of all, we have to create a stack which is the total number of vertices of the original graph is having. Now choose any one vertex as the starting point of the traversal and push that vertex into the stack. Then after that, push a non-visited vertex to the top of the stack, Now repeat the steps 2 and 3 until no vertices are left to visit from the vertex on the stack top. If no vertex is left, go back and pop that vertex from the stack. So repeat 2, 3, 4 until the stack is empty. So while we are going to represent by using example, we are going to explain this. So now DFS, this is the graph, and here starting, this is the started node, and from that A, B, C are adjacent vertices. So now we are just moving from S to A, either A or B or C. So let us consider any one of these vertex. So S to A will move, and A adjacent is D. So then we'll move to the D. D adjacent is G, and G's adjacent is either E, F. So any one from this we can consider. So first we'll go for E, then E adjacent is only B, then go to B, then there is no adjacent, so backtrack to E, and no adjacent, already vertex is repeated, go back to G, then the adjacent leftover is F because it is not visited, then we'll move to this, and next after that we'll move to C. So wherever the dotted lines will be there, then that is nothing but the required spanning tree. Then elaborately we are going to discuss by taking an example of this. Now let us say, so this is the given graph and we are going to initialize this stack. Now from where the step 1 is, we are going to initialize this stack. Then step 2, we have to consider any node from where we are going to start. So that node we just put into the stack. So mark S is a visited and put onto the stack. Explore any unvisited adjacent node from S. We have 3 nodes and we can pick any one of them. For example, we can consider in the alphabetical order. So we can consider in the next step, we are going to consider then the adjacent vertex is, let us say, A. So A is visited. So then we can put onto the stack, explore any unvisited adjacent node from A. So we are going to put A onto the stack, because anyone we can select, either A, B or C. We are going to select A. So once if you are going to select and once we push into this stack, then the top of the stack is A. Then the next step, we are going to verify what are the adjacent vertices to A. So which are not visited, So here from A there are, so the vertex D is adjacent, then we can push them into the stack. Then we just kept here. Then another one is from D, and then we have to move the next step. So from D, so there are adjacent vertices are B and C. Then if you are performing, see here up to here, the stack will be there. Then we have to consider any one of these 2 vertices. These 2 vertices are not visited. So for the alphabetical order, so we can visit B and we can push the B vertex into the stack. Now from B, there are adjacent vertices, only one vertex will be there. This is already visited. So unvisited nodes are not there. So we find, just we are going to pop B. That means we are going to move towards a backtrack. So then we will move to D. And we just pop the vertex B. And now another one is from D. Then the adjacent vertices which are not visited is only C. Then we are going to consider, we push into the stack, and then from C there is no other vertex. There is no adjacent vertex. Adjacent vertex is S is there, but S is already visited. So C do not have any unvisited adjacent node. So we can keep on popping the stacks until we find the node that has visited adjacent node. In this case, there is a none, and we can keep on popping until the stack is empty. So we pop D, C, and then we go back to D, and then there is no adjacent vertex remaining. So we pop D also. Then we go for A, and A there is no adjacent vertex which is not visited. So we pop A also, and then again the another one is S will be there, and then from S also there is no adjacent vertex from that. So we are going to pop that. So subsequently we can get, so this is the way that we have to find out the minimum spanning tree. So from this the corresponding spanning tree is, let us first we started with from A, S, and then we just move to A, and then we move to D, then we move to B, then we backtrack, and then we move to C. So this is the final spanning tree by using DFS. Now let us go for finding the spanning trees by using DFS for this graph. Let us say G is the graph. Now, so let us starting one vertex, let us say V1 is the vertex, starting one vertex. So from this there are so many adjacent vertices are there. So here we are going to take the starting vertex S into the stack. Then after that V2, V3, V6 and V4 are the adjacent vertices, then we are going to consider V2, push into V2 into the stack, then we are going to consider the corresponding edge, V2. So after that, the adjacent vertex is a non-visited adjacent vertex is a V7, then we just move to V7, then after that, there are two adjacent vertices it is having. One is V3 and another one is V5. Then we can consider V3. Then, so we are going to take V3 and then, so V3 we are considering. Then after that, there is no adjacent edge. Adjacent vertex will be there, V1, which is already visited, So we cannot consider that vertex. So we are going to pop that. We are going to popping means we just move towards backtracking and V7, and V7 adjacent vertex is V5. So we have to consider V5. So once V5, if you are going to push into that V5, so then V5, from the V5, there is no other vertex, adjacent vertex, then we have to pop this vertex V5, and then V7, from the V7, there is no adjacent vertex, then just you pop this, and once again V2 will be there. V2 already adjacent vertex there is no adjacent vertex, and then you just pop this, and then we reach the starting vertex, and from the starting vertex there are some more adjacent vertices are there. One is V4 and V6. So then, so among these two vertices, pick any one vertex. So then you have to push that vertex into the stack. So we just push V4 into the stack, then V4 adjacent vertex is V8, then V8 is a push into the stack, so we are going to have V8, and then after that the adjacent vertex is V6, then V6 also push into the stack, so we are going to get V6. From there the adjacent vertex is V1, V1 is already visited, then we'll backtrack. While moving backtrack, just we have to pop V6, then we are having V8. So from that V8, there is no other adjacent vertex, and once again pop that vertex V8, and then go back to the V4, and V4 there is no adjacent vertex, and then move to the root vertex where you enter. From that there is no other vertex which is adjacent and which is not visited, so the stack is empty. Then we are considering whatever the graph we are going to get, that is nothing but a spanning tree. That is the required tree, which is nothing but which is having all vertices. So it is nothing but the spanning tree of the original graph. So this is the required spanning tree by using the DFS algorithm. Now let us go for the another one is BFS. So breadth first search algorithm. So from this also we are going to find the spanning trees. So from this we are going to have, so Q we are going to consider. So here the step or rule 1, visit the adjacent, select any one vertex. So from that vertex you have to consider all the adjacent vertices, and we have to consider all the adjacent vertices and insert into the queue. Then from there, these are the three adjacent vertices will be there, and from this anyone you select. So you are just moving to A, and we are going to consider whatever the adjacent vertices will be there, and then you have to push into that Q, and then the next into that we have go for the next adjacent vertex, and then we have to push into that Q, and then we have to, that means if then we go for this C, and once again we have to consider the adjacent vertex. Like that we have to move. Then once again we'll go back, and D, from D we have to consider the adjacent vertices into that Q, and next if there is no adjacent vertex into the Q, no adjacent vertex is found, then remove the first vertex from into the queue, repeat the step 1 and step 2, rule 1 and rule 2 until we are going to get the queue is empty. So here let us go for, we are going to explain with an example. So initialize. Let us first initialize the queue. So queue is not having any this thing, any entry, and now we start from the visiting node is yes, and we mark that as a visited one. So we will mark this as a visited one, and then we have consider it is having 3 adjacent vertices. Then we see that unvisited adjacent node from yes. In this example, we have 3 adjacent nodes, and but alphabetically we can choose A. And we mark that as visited and enqueue that. We are just keeping that into that queue. And next, from this, the next one is the next unvisited vertex which is adjacent to yes. So that is B, and B is, we are going to visit that B and we enqueue that. B. Earlier we enqueue A, now we enqueue B. And now the step 5, next the unvisited adjacent node yes is C, and then we are make that as a visited, and then we will make enqueue into that. That means next from that, so now yes is left, no visited. So here is a yes is going to be. Now yes is having all the 3 adjacent vertices, and there is no adjacent vertex. So we can now yes left with no unvisited adjacent node. So we DQ and find A. So here we are going to DQ then the A, and we are going to find then any adjacent vertex from that A will be there or not, we have to find out. So from that, so D will be there adjacent to A, then we make that vertex as a visited vertex, and we put into the queue, enqueue into that. So enqueue into that. So now once again we are going to consider B, and for that there is no other adjacent vertex which is not visited. Then we go for C. Then C also does not have any other vertex which is going to visit. So we have to remove these things from the queue. So first is a B, next is a C, and next D. At this stage we left no unmarked, no unvisited nodes. But as per the algorithm, we keep on dequeuing it. We get the all unvisited nodes. When the queue gets empty, then the program is over. That means we have started from yes, and yes to A will be, and A to B will be, and B to C will be. Then so first we are DQ A, and we are going to consider, and the next one is D, and the next B adjacent vertex will not be there. So next we consider for C adjacent the vertex will not be there. So A adjacent, then we go for D adjacent is not there. So we are also going to DQ this, and we are going to get this is the corresponding spanning tree. Now let us go for this BFS. For this graph, we are going to find the a spanning tree. So first of all, so yes, V1 is the vertex which is not visited. So make that is a visited vertex, and we have to consider what are the adjacent vertices will be there. All the adjacent vertices into the queue. What are the adjacent vertices? Let us say having V2, and this is having V3, and this is having V4. First let us go for V2, and then we just start queue V2 first, and then after that V3, then we are going to take it as V2 as well as V3. Then we are going to consider next V4 like this. We have to put all these things into the queue. And next after that, the first one is V2 we are going to DQ. See here how we are going to keep. So S is make S vertex as a node. So it is starting from the vertex node and we are going to make it as a visited one. And then we go for the remaining adjacents and then we are going to enqueue that. We are going to enqueue that. In the same way, V1 is making a visited and then all the adjacent nodes were in the alphabetical order. So we are going to V2 and we are going to V3 and we are going to V4 one after the other. One after the other we put into the queue. So from there the next DQ we are going to follow with the alphabetical order. From VQ the adjacent vertex is V7, so which is not visited. So V7 put into the queue. We put into the queue. Let us we are going to have, let us say V2, first V2, then I am considering in the alphabetical order V3, then we are going to consider it as V4. V1 we are going to select. Then we have to remove then V2 because V2 we are going to select the next time. We are going to DQ that and then V2 adjacent vertex is V7, make V7 into the queue and next from V7 then there is no other. So V2 to V7 will be there, then V2 we have to remove that. Then we consider for V3. So V3 adjacent vertex is V7. V7 already visited and V1 is already visited. So DQ that and next go for V4. V4. So V4 unvisited is V8. So V8 adjacent. So then we'll make it as V8. We'll make it as V8. So now we'll move to the next one which is there in the stack V4. V4 adjacent is already we consider V8 and then we are going to DQ that. Then we consider for V7. V7 adjacent is V5. Then we put into the stack V5. We put into the queue V5. Then and we are going to, there is no other vertex which is not visited. So V7 and then remove V7. Then next is V8. V8 adjacent is then we are having one vertex. Let us say it is V6. So V6 enter into the queue. Then V6 enter into the queue. Then there is no other adjacent vertex to from V8. Remove that and go for V5. V5 there is no adjacent vertex. So remove from stack and then V8. V6 also there is no adjacent vertex. So which is the required spanning tree. Which is the required spanning tree by using the BFS. By using BFS. So we are having the BFS spanning tree is this. BFS spanning tree is this. Now let us go for taking one example for this. This is the graph. So for this graph, we are going to find DFS spanning tree and a BFS spanning tree for this. So from this, let us go for any one starting vertex. Let us go for the vertex is A. Vertex is A. So now from this, there are first we are going to proceed with the DFS. So we are going to proceed with BFS, let us say. So BFS in the queue, let us say, make that as, make A vertex as visited, then the remaining are B and D. So first of all, we are going to take B as the visited node, B as the visited node, and we are going to keep into the stack. So after that, the other one is D. So once again, we are in the next step, we are going to consider the D is also. So we are having like this stack we are having. Then we are just keeping D is also into the stack. And now, so this we are going to consider. So after that, there is no other vertex which is not visited, So B is visited and make vertex B is visited and D is visited. Now let us go for B. So B is the beginning, which is a beginning vertex into the stack. So now concentrate on B, and next what are the adjacent node? So adjacent vertex is C, and we will make it as a visited, and then we will put into the queue. C. Then there is no other vertex from B, so we are going to remove that. From that, and next we have to consider next value is D. So from that D, and what is the adjacent vertex is only E. So have to consider the corresponding edge and make the vertex E as a visited one, and then we will put that into the stack. Then after that, then we are going to remove, there is no other. So then go for C, and C, from C adjacent vertices are E, D and B, E, which all are visited. So I am going to remove that. I am going to DQ from the DQ. So the next is E, and E adjacent vertices are F and G. So we can consider one is F and another one is F. I will consider first, and then I am just taking the next one is G. So next we have to consider G. Then once from F. So here we have, I am going to redraw that. So here A, B, and then C I am going to get, and I have D, and I have E, then E2, then I am going to have F, then I am going to have G, then E, there is no other, so I am going to remove that. Then the remaining is F will be there in the stack. F adjacent vertices are H only, so we have to consider H and make that is a visited one, and we will enter into the queue H. So from this G, and next is G, F, there is no other vertex, so remove that, and next DQ that, and next G will be there. G adjacent vertex is only H will be there, but H is also visited one, so there is no other from G, so remove that. Then I am going to have H now. H adjacent vertices are from these three, anyone we can select. So I can go for alphabetical order. So I am going for first is I, then the another adjacent vertex is J, the I J, then another adjacent vertex is J, we have to enter, then the other one is K, we'll make it enter into the stack. Then from the H, there is no other adjacent vertex, so remove that. Now we have the K, I, J, K's are there in that Q. Now we have to consider the next vertex is I. From the I, there is no other adjacent vertices, so remove that, and then J will be there. From J, only K is adjacent, but it is already visited, and I cannot connect this. If I connect this, I am going to have a loop, so remove that from the Q, and then I have a key K, and K is from K, there is no other vertex to visit, so then I am going to DQ that. So simultaneously I am having a spanning tree, then this is the corresponding spanning tree. So by using BFS algorithm. So here BFS spanning tree we are having from the previous graph. And now let us go for the same, and we have to consider what is the DFS. So from that, and we have to consider the DFS spanning tree for this. So while we are going to consider the DFS spanning tree, then we have to consider the stack. We have to consider the stack, and based on that, we are going to move that. So here, let us A will be there. So A is the starting node, and from this, and B and D will be there. And I'm just following in alphabetical order. I can follow the D also. If I'm going to move to B, then I have to get B from this. So then I'm just having see this here how we are going to move DFS. So DFS, whatever we are going to select from the stack, then I am going to consider all the adjacent nodes, of the top wherever we are going to find, and if there is no adjacent, then we'll go to backtrack. When we are going to backtrack, then we are going to apply the pop operation, and whatever the top element will be there on the stack, then we are going to remove that, and we are going for the next vertex. From there we are going to backtrack. So in the same way, then we have to consider, so B will be there, and I am going to consider, so put B into the stack. Then after that, then B adjacent vertex is C will be there. Then we have to put C, vertex of C, we made it as a visited, and put into the stack. And after C, then there are so many, either I can consider E, I can get one type of, either I can consider D, another type. Both are correct, but I am just following in the alphabetical order. So for that, the adjacent node is D. So I just put into the stack, then I will consider that D, and then the adjacent node from D is, then E will be there, which is not visited. Then I have to keep E, and from there, and F and G will be there adjacent, and then I will consider any one of these two. So I am just to consider F will be, and F on adjacent vertices are, one is G, and another one is G, and another one is H. So I am just moving G, I'll move to G, I have to consider that edge G. Then from G, then I am going to move, then the adjacent vertex is H. So I will consider that H also. Then, so among this, next I, J, K are adjacent vertices, and in that anyone we can select, the alphabetical order sake, I can go for I. So I am moving towards I. Then there is no vertex to C. Then I will move backtrack. There is no adjacent vertex to from I, means I am going to remove from that, and then I will search for another. Adjacent vertex from H. So from this, there are two adjacent vertices are there. From this, we are going to select. We are going to select J, and then we have to push J into the stack. And from J, and there is a adjacent vertex, that is let us take it as a K, and K put into the stack. So K adjacent vertex will be there. One is H is already visited, so there is no adjacent vertex from K, and then we just pop that. Going back to J, then we cannot find any other adjacent vertex from the J. Then, and we are going to remove J vertex from the stack, and then we go for next is H, and from H also there is no, and then we go for G, and G also there is no other vertex adjacent other than the visited vertex. Then we'll just move backtrack, and then F, and then E, then we'll go for E, and we'll then go for D, then E is not having, and once again D, which is not having, then go for C is also not having, then go for B, then B is also not having, then we'll go for the initial vertex which is already visited. Then from there is no other vertex. So it is known as a DFS spanning tree. DFS spanning tree. And this is known as a BFS spanning tree. So this is a BFS spanning tree, and then we have to consider this is a DFS spanning tree. DFS spanning tree, which is similar to our spanning tree. So this is the way that we are going to construct how we are going to construct a spanning trees by using DFS and BFS. So DFS, whatever we are going to consider the vertex, from that adjacent vertices, while we are going to consider either B or D, anyone you can consider, but alphabetical order sake I can consider B. So from B you have to go deeper and deeper. So B, then we have to find C, and from there we have to find D, from there we have to find E, from there we have to find F, from there we have to find either F or G, from there we have to find G, and from there we have to find H, and there we have to find I. Then there is no other backtrack, and then we'll move the next any one of these adjacent. So you can consider J, then we have to get from J, K we have to get, and from there is no adjacent, while just we are moving, tracking all the things and keeping the elements into the stack. That means the order how we are moving, how we are going to traverse the vertices. For showing those, we are going to take the stack and we are going to verify for each and every backtracking whenever we are going to occur, and we are going to remove the element which is there in the stack, and from there we are going to verify once again any adjacency, non-visited vertex is there or not. If it is there, and we can traverse that. If it is not there, simply we can remove that vertex from the stack. So the process will be continued. The process will be continued until we reach wherever we started. Until we reach wherever we started. And while we are going to coming to that also, we are going to verify any other adjacent node will be there or not. If there is no adjacent node, then we can stop. And if there is another adjacent node from the where we are started, from there again the process will be continued, which is there in DFS, But BFS, we are going to consider the queue, while just a queue and the order, how we are going to, while considering the node, from the node adjacent vertices, we are going to keep all the adjacent nodes, we are making it as visited, and we are going to keep into the queue, the way that we are going to consider. So for suppose B node you are going to make it as visited, and next B node, and after that D node if you are going to consider, then we have to put these two vertices into the queue. Then I have to, from these two, which one I have to consider? So I am going to consider B, and then we have to consider the which adjacent node that we have to see, we have to traverse. So I am going to consider C, and C node we are just keeping into the queue, and next after C, after keeping B adjacent is C, then which node we have to consider? So we have to consider D. So from that D we have to take E. So once again we have to keep that vertex into the queue. Then we are going to remove that, and next C, from the C, and if there is only one vertex will be there, CE, and which is adjacent but is already visited, so I am not going to consider. Next I am going to consider E. So from the E I am going to take E, F and G's will be there, so I have to consider first F and then G, then I have to consider. After that there is no, then I am going to DQ that, then I have to consider F, So from F, whatever the adjacent vertices which are not visited, so it is nothing but H will be there, so I have to consider H, then I am going to remove that. So next G will be there, G adjacent is only one which is already visited, so I am not going to consider. Then H I have to consider. So from H there are three adjacent vertices, one is I, another one is J, and another one is K. In this order I am going to consider, so that I am going to remove after considering this. Then I, from I, there is no other vertex to visit. So remove that. And next J, from there J, there is no other vertex. The way that how you are going to remove the vertices, the same order we are going to the corresponding edges we are going to add. We are going to add. Subsequently, we are going to get the corresponding until the process is going to become continued until either it will be a stack or it will be a queue. It will be empty. The process will be continued till either stack or queue. It is going to be empty. So ultimately, whatever the trees we are going to get, those trees we are calling it as a either we are going to apply DFS, that is a DFS spanning tree, or if you are going to consider BFS, then it is known as a BFS spanning tree. So this is the way that we are going to find the spanning trees by using BFS and DFS. With this I conclude. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.